Hello, this section is acceleration. Let's get started. The pitcher throws the ball speeds towards the batter. Off the bat it goes. It's going, gone. A home run. Before landing, the ball went through several changes of motion. It sped up in the pitcher's hand and lost speed as it traveled toward the batter. The ball stopped when it hit the bat, changing directions, sped up again, and eventually slowed down. Most examples of motion involve similar changes. In fact, rarely does any object's motion stay the same for very long. What is acceleration? Suppose you are a passenger in a car stopped at a red light. When the light changes to green, the driver steps on the accelerator. As a result, the car speeds up or accelerates. In everyday language, acceleration means the process of speeding up. Acceleration has a more precise definition in science. Scientists define acceleration as the rate at which velocity changes. Recall, the velocity describes both the speed and direction of an object. A change in velocity can involve a change in either speed or direction, or both. In science, acceleration refers to increasing speed, decreasing speed, or changing directions. Increasing speed. Whenever an object's speed increases, the object accelerates. A softball accelerates when the pitcher throws it, and again when a bat hits it. A car that begins to move from a stopped position or speeds up to pass another car is accelerating. People can accelerate too. For example, you accelerate when you coast down a hill or on your bike. Decreasing speed. Just as objects can speed up, they can also slow down. This change in speed is sometimes called deceleration or negative acceleration. For example, a softball decelerates when it lands in the fielder's mitt. A car decelerates when it stops at a red light. A water skier decelerates when the boat stops pulling. Changing directions. Even an object that is traveling at a constant speed can be accelerating. Recall, the acceleration can be a change in direction as well as a change in speed. Therefore, a car accelerates as it follows a gentle curve in the road or changes lanes. Runners accelerate as they round the curve in a track. A softball accelerates when it changes directions as it is hit. Many objects continuously change direction without changing speed. The simplest example of this type of motion is circular motion, or motion along a circular path. For example, the seats on a Ferris wheel accelerate because they move in a circle. Calculating acceleration. Acceleration describes the rate at which velocity changes. If an object does not change in direction, you can describe its acceleration as the rate at which its speed changes. To determine the acceleration of an object moving in a straight line, you must calculate the change in speed per unit of time. This is summarized by the following formula. Acceleration equals final speed minus initial speed divided by time. If speed is measured in meters per second and time is measured in seconds, then the SI unit of acceleration is meters per second, or meters per second squared. Suppose speed is measured in kilometers per hour and time is measured in hours, then the unit for acceleration is kilometers per hour, or kilometer per hour squared. To understand acceleration, imagine a small airplane moving down a runway. Figure 10 shows the airplane's motion after each of the first 5 seconds of its acceleration. To calculate the average acceleration of the airplane, you must first subtract the initial speed of 0 meters per second from the final speed of 40 meters per second, then divide the change in acceleration by the time, which is 5 seconds. Therefore, acceleration would equal 8 meters per second squared. So this airplane accelerates at a rate of 8 meters per second squared. This means that the airplane speed increases by 8 meters per second every second. Notice in figure 10 that after every second of travel, the airplane speed is 8 meters per second greater than it was the previous second. You will see here how to calculate acceleration. So acceleration is final speed minus the initial speed divided by time. So our final speed was 22 meters per second. We're going to subtract that from our initial speed, which is 4 meters per second, and then we're going to divide that by 3 seconds. So we have 18 meters per second divided by 3 seconds, and our acceleration is 6 meters per second squared. Graphing acceleration. Suppose you ride your bicycle down a long, steep hill. At the top of the hill, your speed is 0 meters per second. As you start down the hill, your speed increases each second. You move at a greater speed and travel a greater distance than the second before. During the 5 seconds it takes you to reach the bottom of the hill, you are an accelerating object. You can use both a speed versus time graph and a distance versus time graph to analyze the motion of accelerating objects. Speed versus time graph. Figure 11 shows a speed versus time graph for your bicycle ride down the hill. What you can learn about your motion by analyzing this graph. First, since the line slants upward, the graph shows that your speed was increasing. Next, since the line is straight, you can tell that your acceleration was constant. A slanted straight line on a speed versus time graph means that the object is accelerating at a constant rate. You can find your acceleration by calculating the slope of the line. To calculate the slope, choose any 2 points on the line, then divide the rise by the run. In this instance, you would pick 8 meters per second minus 4 meters per second and divide that by 4 seconds minus 2 seconds, and that equals 2 meters per second squared. During your bike ride, you accelerate down the hill at a constant rate of 2 meters per second squared. Distance versus time graph. You can represent the motion of an accelerating object with a distance versus time graph. Figure 12 shows a distance versus time graph on your bike ride. On this type of graph, a curved line means that the object is accelerating. The curved line in figure 12 tells you that during each second, you traveled a greater distance than the second before. For example, you traveled a greater distance during the third second than you did during the first second. The curved line in figure 12 also tells you that during each second, your speed is greater than the second before. We recall that the slope of a distance versus time graph is the speed of an object from second to second. The slope of the line in figure 12 gets steeper and steeper. Since the slope is increasing, you can conclude that the speed is also increasing. You are accelerating. We have now completed our reading for this lesson 2. You will need to complete the next pages as your homework. Thank you. See you all next time.